So we discussed in the last video that heat is one form of energy, and it's associated with the temperature of an object. More specifically, what we're looking at when we're discussing heat is when we have energy being transferred as a result of a temperature difference. So if we have two different things that are at different temperatures and they're in contact with one another, they're always going to be transferring energy from one to the other, specifically from the thing that's hot to the thing that's cold. So when we're thinking about energy moving in a chemical reaction or in a system of any kind, we can think of heat as one of the two ways that energy is transferred. Now, in reality, it's a little bit more complicated than we're going to look at in this chapter. We're going to simplify things quite a bit. But for our purposes, we are going to only think of heat and work. And we're even going to simplify things more than that, because we're actually only going to be looking at one kind of work as well. But we'll get to that later. For now, let's just remember that when we're thinking about transferring energy, we're either thinking about work or we're thinking about heat. Those are the only two ways we have of moving energy around in a system. So before we talk about heat some more and how we're going to move this around, we're going to need to define what happens to energy in our chemical reactions. More specifically, we need to make sure that everyone understands that when we have energy moving around in our chemical reaction, we can't lose it and we can't gain any extra. Whatever happens to the energy in a chemical reaction, we are not creating energy, we are not losing energy. The only thing that we can do is move it and transform it. So we can move it from one place to another, and we can change it from one kind of energy into a different kind of energy, but we cannot create or destroy the energy. This is what the first law of thermodynamics states. This is the law of the conservation of energy. Energy cannot be created nor destroyed. So, as you can see here with this lady, who's pushing what looks like a bowling ball onto this spring, which does not seem like a very bright idea, but it's good for our example here. Push the bowling ball down. That puts mechanical potential energy into the spring. So there's energy stored in the spring. And when she lets go of the bowling ball, the spring shoots the ball up into the air. So the energy that was put into the spring is no longer there. So it's been transferred into the bowling ball, which is now shooting through the air. Not only has the energy been transferred, but it's also been transformed. It's been changed from one form of energy into a different form of energy. So it was changed from the mechanical energy in the spring to kinetic energy as the ball is moving through the air. And we do this literally all the time, constantly. Constantly we are doing this. Right now, you sitting in your seat, even if you're doing nothing other than just sitting there listening, your heart, as it's pumping and pushing the blood around your body, it is converting chemical potential energy into kinetic energy. It's taking molecules, and I'm not a biologist, so I'm not going to try to get into all the specifics of what kinds of molecules they are, but it's taking molecules, molecules that your body can use for energy, and it's converting those molecules into the energy that it uses to pump that blood throughout your body. So it is converting energy from one form to another. We are constantly doing this all the time. And we don't really ever think about, do we lose energy? Do we waste energy? And the answer is yes, we waste energy all the time, but we do not lose it. We can never create or destroy it, but we can waste it. Energy can definitely go to waste. Alright, so if we're not creating or destroying the energy, where does it go? Well, we are going to define, anytime we're thinking about energy and a chemical reaction, we are going to define the system as the material or process within which we are studying energy changes. So essentially the thing we're interested in. that is our system. Now, most of the time for us, that is going to be a chemical reaction or a very specific object. So we'll see a few examples, like we have a penny that's heating up or cooling down. In that case, the penny would be our system. Or if we have a chemical reaction, like maybe we mix some acid and base together, then the system would be those molecules reacting with one another. So we have our system, which is the thing that we are interested in. Literally everything else is the surroundings. Now, that includes literally everything else in the universe, but realistically it's just everything nearby. Everything that the system can exchange energy with. So when we're talking about energy moving around, the energy is always going into or out of the system and surroundings. So if the system is gaining energy, that energy didn't just come from the ether. It came from the surroundings. Because again, we can't just create or destroy energy. The energy, if we're gaining energy, had to come from somewhere. If we are creating energy and losing it, it has to go somewhere. It doesn't just kind of sit there and be like, well, here I am. I am created. Woohoo! No, it has to go somewhere. It's going to go. It's going to move somewhere. And so energy is constantly moving either into or out of our system and surroundings. And because we know the first law of thermodynamics, we know that the total amount of energy in these two things must be constant. So if, for example, we have our system that starts off with 2 energies, you can see here, and the surroundings has 1, and some type of reaction occurs, and now our system only has 1 energy left, we know for a fact the surroundings must now have 2. Because again, the total amount of energy must stay constant. We can't create or destroy energy. Alright, so speaking of energy, if we're going to start actually quantifying this stuff, we need some units to go along with it, because everything needs units. When it comes to energy units, there are really 2 main units. One is slightly more used than the other, though. The one that is slightly more used is what's called a joule. And a joule, which is see, do I have it written somewhere in here? There it is. Should have it written larger somewhere. But a joule is derived from the equation for kinetic energy. So if you've taken physics, you're very familiar with this equation. And if you notice here, we have a mass times a velocity squared. And if your mass is measured in kilograms and your velocity is in meters per second, the units that you get for kinetic energy are going to be kilograms meters squared per second squared. And so this comes up all the time, and it is an amount of energy. And so just to simplify things so we don't have to be constantly writing kilogram meter squared per second squared, scientists decided to say, yea verily, 1 kilogram meter squared per second squared henceforth shall be known as 1 joule. And so 1 joule is 1 kilogram meter squared per second squared, which is not a whole lot of energy actually, but it's not minuscule either. Other units that are going to be commonly used are calories. And these you're more familiar with, although the calorie that we are going to use is actually not the calorie that you're familiar with. The calorie that you're familiar with is the food calorie, which is this one, which for some reason people decided to give the exact same name as the normal, so to speak, calorie, and just say, oh, but it's a capital C instead of a lowercase c. It's like so unhelpful, really not helpful. For our purposes, on exams and things that I myself write, I will always specifically say food calorie if I actually intend for you to use this larger calorie. For the homework, I'm not entirely sure that they will always do that. You might have to pay close attention. If it says kilocalorie, that is saying that's a food calorie. Because a food calorie, what you read on a box of cereal or on a can of pop, that is actually 1,000 of these normal calories, these scientific calories. So a lowercase c calorie is 1,000th of a food calorie, and a lowercase c calorie is also 4.184 joules worth of energy. So a calorie, even this smaller version of the calorie, is still over 4 times as much energy as a joule. So the calories are a bit bigger than joules. Another unit that you are probably familiar with, especially if you own a home, is kilowatt hour. This is what you will measure your electricity bills in. How many hours worth of time did your house use a kilowatt worth of power? So a power unit times a time unit gives you an amount of energy. And a kilowatt hour is over 3.5 million joules. So it's a big unit. It's a lot of energy. And as you can see here, down on this table at the bottom, first of all, you can get just the comparisons between all three of these. So 1 small calorie is the same as 4.18 joules, which is the same as 1,000th of a big calorie, which is the same as 1.16 times 10 to the negative 6 kilowatt hours. But you can also see the amount of energy that it takes to do other things that you probably do in your everyday life. So like, for example, running a mile. It takes about 100 food calories, and that'll be a little bit different from one person to another, but it's approximately 100 food calories to run a mile. The amount of energy that you use in a day is about 22,000 food calories. Or sorry, not 22,000. That would be is that 220,000? I think that's right. I'm doing that math right in my head, yeah, because the 5 would be 100,000. So 220,000 food calories worth of energy per day is what you would use. So this would be like you going about your everyday life and like driving in your car and the electricity that you would use and all that stuff. Because you yourself personally only use about 2,000. If you're anyway, if you're an average sized person, that's the I don't know if it's the CDC that sets that or not, but like the average human person is supposed to use about 2,000 calories a day, which is why the recommended calorie count for the average person is 2,000 calories a day. So this is obviously a lot more than that, but you use a lot of energy doing other stuff in your life. But it does kind of put in perspective exactly how much energy it takes to run you as a person. Like your body burns an incredible amount of energy every day. As you can see here, you can heat up a gram of water, which given is not a whole lot of water, but let's bump that up to 1,000 grams, which would be a liter of water. So a liter of water, you can heat that liter of water up by 1 degree C, which is significantly larger than 1 degree Fahrenheit, if you remember, with just a single food calorie. And you burn 2,000 of those things every day, just being your everyday normal self. So it takes a lot of energy to run you, which is pretty crazy to think about. And we get that energy by eating tacos. Anyway, kind of fun to think about, I think, anyway. Alright, so then just to remind you once again here, the first law of thermodynamics, we said that thermodynamics is the study of energy and its interconversions, and that first law told us that we cannot create or consume energy, we can only move it around. The total amount of energy in the universe is constant. There is no free lunch. We can't create energy from nothing. If we get energy from something, then that something has now lost that energy. think we'll go ahead and call it here for this video. In the next one, we're going to talk about internal energy and a interesting thing called a state function. So we'll pick up here next time.